thesis defense. I'm Leslie Kelbling, one of his supervisors. We also have Josh Tenenbaum here and Tomas in the ether, and George is on the committee. And this is a kind of a good family of Toms here. Let me say something about the process. So Tom will give a talk. We'll ask a few questions as he gives a talk. We'll also have the audience ask a few more questions after that. Then we'll excuse everybody but the committee, and we'll talk to Tom separately. You're welcome to hang out in the lobby. And then when Tom emerges victorious, we will have cake and champagne. So that's the plan. So we're happy and sad for Tom to be finishing. He showed up already, like really intellectually grown up. And so that was awesome. And he's been the kind of student who walks in my office and says, oh, here's this thing I did. And oh, that's pretty cool. And so he's done just this incredible succession of cool things that combine a bunch of different ways of thinking, and most recently run on real robots and make Spot the robot do cool things. And so we're very enthusiastic. Josh might want to say a word or two, and then we're going to go.
Okay. Yeah. I'm only happy.
But it doesn't mean I'm just teasing, but it doesn't mean I won't miss you a lot. No, there's lots of nice things I can say about Tom. He's really smart. He's really nice. He's a great community member. He's really good at collaborating with people. He's really good at being mentored, and he's really good at mentoring. I've seen him in all of these contexts, so I know he's going to be an awesome professor at one of the many jobs that he has been offered. I'll just say a special thing about Tom that goes back to the first time I met you, and in some of the conversations when we were, before you even got here, when we were thinking about your plans. You know, I met Tom when he was working at Vicarious. I think that's when we met, right? Which was this AGI company. They were very interested in many of the same things that Leslie and I and a lot of us are here. You know, well, how does intelligence work in general, especially in human minds or animals' brains? How can we build that in machines and be guided by what we know about natural intelligence? But Tom was different. He seemed really actually motivated by that. He really wanted to know, like, what's built into babies' brains and how do children learn? And what about these crows? And they're so smart the way they use tools. And he came into grad school with big ideas about wanting to be guided by what we know. There's a lot we don't know, but there are some things we do know about how babies start, how children learn, how many brains, not just human brains, think about the physical world and objects. What's distinctive maybe about humans for long-term planning and symbolic stuff. And he was really interested in all these big things. And he was consistently motivated and able from the very beginning to connect the dots between really big conceptual questions and actually getting stuff done, right? And actually like he's going to talk to you about things that involve like long-range planning, but he is really good at long-range planning. Like having a goal and working backwards, like what are the sub-goals, what are the sub-goals, and how do I actually implement the low-level actions that can achieve that over, a PhD is a long time, 5-6 years, including all the time to this point. More than that, right? Yeah, I mean, because it's a long time, long-range planning problem. And to connect like the North Star goal that you have and all the stages and all the things you need to do beyond just being smart, being nice, and working with people, and also at the same time, like figure out how to get a job and get some. It's really just, I think it should be an inspiration to all the students here and to me, honestly, so to many of the faculty. So anyway, thank you for the opportunity to work with you, to learn with you and from you, and really excited to see you bring all the pieces together.
Thank you so much. Incredibly kind introduction. I'm overwhelmed, and thank you all for being here. It's a wonderful turnout. So yeah, I'm really excited to tell you about some of the work I've done over the past 6 years in my PhD. And I'll start by saying, so this is a Spot robot that we've been working with at the Boston Dynamics AI Institute. And in my work, I'm trying to develop these learning and planning techniques so that we can give Spot goals like, hey, Spot, put away the tools. And then Spot will quickly start to take actions towards achieving that goal. So it's going to pick up this measuring tape on the floor here. It'll see that brush on the side. It'll work on putting that away. It realizes it has to retry a couple times when grasping fails. It'll put that drill away. And then it realizes that the hammer there is too high to reach directly, so it needs to plan a different way to reach the hammer. So the goal in all this work is to develop robots that can serve many, many different functions in society. So we want to have robot chefs, robot lab assistants, robot house cleaners, robot beekeepers, among many, many other kinds of very helpful, very general purpose robots. And to achieve that, we're going to need to have a robot factory like Boston Dynamics, for example, that creates these robots like Spot robots. And then these robots will be shipped off to many different kinds of deployments like homes, hospitals, restaurants, coffee shops, and many others. If we think about what's going to happen inside this robot factory, we'll need to create robots that are good in general. We'll be thinking about what are the most common cases that come up across a wide range of deployments. And so the engineers in this factory will be doing a very general purpose kind of programming. And part of that effort these days might be pre-training very large foundation models. So if we look at a lot of the work that's going on in some of these big industry labs today, a lot of it is of this kind, where we're trying to train these very big, very general purpose robot models and really get us ready for what will be the robot factories of tomorrow. But after we have the robot factory, the question will become, what will happen once the robots reach their deployment? And I think what we want is for the robots to become experts in their domain once they're deployed. When I say domain here, I don't mean the domain of household robotics broadly, but I mean we want robots that become experts in your home with your goals and your objects and your preferences and your constraints and everything that's really unique to you. So we're going to want robots that are capable of learning to specialize during deployment. And we're also going to need these robots to be capable of planning and reasoning in the moment, because the world is incredibly complex and unstructured. And if we want to have robots that can do something like clean up an entire room, then we're going to need robots that can really think intelligently and think ahead. These deployed robots need to be efficient and effective in a number of different ways. So first of all, we're going to need these robots to be time efficient in the sense that we don't want them to be kind of philosopher robots thinking for hours about what they're going to do before they take any actions. We want them to start taking actions immediately after we tell them what we want. We also want robots that are data efficient. So we want them to learn a lot from just a little bit, especially if we're doing this during deployment. We're also going to need these robots to be human efficient. So the robots should ask for help, and they should, interact with people intelligently, but they shouldn't be overly reliant on people. They should be autonomous. And we certainly don't want to assume that there's an expert programmer that's deployed with the robot that's capable of intermeeting programmatically. And finally, we want these robots to be effective. So we want them to actually solve the hard tasks that we're giving them. So if we think about some of the paradigms that are available today for this kind of online decision-making in robotics, one paradigm is AI planning, and task and motion planning is an example of that, which I'll talk about today. And planning is great because over several decades of work, we now have these very powerful solvers, which if we give them the right kinds of representations, then these solvers will work really hard to figure out what actions the robot should take. One of the pitfalls of these approaches is that they tend to be slow, especially in large problems with many objects and high dimensionality. But a bigger issue is that to even use these kinds of solvers in the first place, you need to have a variety of different domain-specific models, which are usually programmed very carefully in the lab by somebody like me. And even for me, it's difficult to anticipate how changes in the models will influence the solver performance. So it can be very difficult to design these models effectively. And traditionally, these kinds of AI planning approaches don't involve learning. So as a robot sees the same kinds of problems over and over again, it's not getting any better or faster over time. Another paradigm for online decision-making in robotics, which has made a lot of progress in the last 10 to 15 years, is reinforcement learning. And reinforcement learning is great because at the end of the day, what you get is some kind of big policy, for example, maybe a big neural network, and you give it an observation, and it will give you back an action very quickly. Reinforcement learning is also nice because these are generally applicable domains, broadly applicable. There's a certain amount of human engineering that goes into reward functions and observation and action-based design and so on, but these are broadly applicable approaches. In practice, though, reinforcement learning works best when we have relatively narrow distributions of tasks and when we're thinking about relatively short time horizons. And reinforcement learning is also notoriously data hungry. So the best results that we have are really in cases where we have a simulator that we can use to generate arbitrarily large amounts of data and then really do reinforcement learning more like in the factory versus during deployment. Most recently, there's been a ton of excitement around large language models and other kinds of foundation models and looking at, can we use something like ChatGPT to do some kind of online decision-making in robotics? And we've been excited about this too. We have a couple of works in this direction. And similar to reinforcement learning, there's the prospect that we can be very time efficient because we're talking about a big neural network. We can pass through it very quickly. And what's cool about these foundation models is that they can generalize very effectively. For example, if you give them a couple of examples, then ask them to solve a problem in the same form, then they can do very well in this few-shot prompting regime. There's a certain amount of prompt engineering and validation that goes into using these models in practice, But the biggest issue is that the models that we have today are just not well equipped for solving these very long horizon, very complex robot planning problems. And I'm hoping to give you some intuition for why that's true. But nonetheless, I think these models are very powerful and can be used in a number of different ways. And I'm happy to talk a little bit more about that if you're curious. But what I really want to focus on today is a different kind of approach, which I'm going to call learning to plan and planning to learn with abstractions. And this is going to be an approach that is very time efficient because we're going to learn from past planning experience to make planning faster in the future. It will also be data efficient because we're going to be doing a very structured kind of learning that allows us to generalize a lot from just a little bit. It will be human efficient because we're not going to be hand designing these domain specific models, but instead learning them automatically. But we'll be learning these models in a way that allows us to take advantage of these very powerful solvers from AI planning. So it will be very effective as well. So let's jump in and let me start by explaining what do I mean exactly when I say planning. So at the end of the day, we're going to have a robot like the Spot robot, and we're going to give it a goal, like put away the tools. And so we have some kind of initial state and we have some goal, and we're going to want to have a planner that's capable of sequencing together these actions to eventually achieve the goal that is given. And the question is, what's going to be happening inside this planner? Well, first of all, robots have sensors. So this robot happens to have cameras in its hand and some on its body. And so we can take images from those cameras, and then we can use advances from computer vision to construct a nice structured object-centric view of the state. So we can detect, for example, that there's a hammer, and we can detect certain features of these objects like position and so on. And from tracking and detecting these objects, we can construct this nice view of the state where we know that there's a hammer, we know there's a bucket, the robot itself is an object, and we are detecting these features of it. So this is already introducing quite a lot of structure. And so rather than just thinking about this state arbitrarily, we're going to say we're thinking about these object-centric states. But even so, we still have a very difficult decision-making problem inside this planner. And that's because we're going to be reasoning over very long time horizons. We have these continuous states and actions, and we only are giving the planner a goal. We're not giving it any kind of reward or cost function that would be helpful for giving some kind of dense guidance. So to make this difficult decision-making problem more tractable, we're going to introduce a kind of state abstraction. And it'll be a particular kind of state abstraction that uses what are called predicates. And the hope here is that rather than thinking directly about the low-level states, the planner can kind of focus on what's most important at this abstract level first. So what are predicates? Predicates are relational classifiers over object states. So for example, let's take a look at this block stacking domain where there are these 5 blocks and the robot itself is another object. And so we have this object-centric state shown in the table there. And here are 2 example predicates that we might have in this domain. One is called onTable and the other one's on. So onTable is shown in the top there. And the definition of this onTable predicate is it takes in a current state like the one on the table, and it takes in an object like a block, and it simply looks at the z position of that block to make a very simple definition of what it might mean for a block to be on the table. So it says, is the z position less than some threshold? If it is, then the block is on the table in this state. And then we have on, which is a binary predicate. It takes in 2 objects, and it compares their positions and sizes to decide whether one is on the other. Again, a very simple definition of what it means to be on. So if we have these predicate classifiers, then what we can do is we can run them over all combinations of objects in a given state and record all of the classifiers that evaluate to true. And that's what's shown in this abstract state here. This is the set of all true ground predicates in the low-level state. So you'll see we've thrown away all of the continuous information in the state. We've potentially lost useful information that we ultimately want to use to decide what actions to take. But the hope is that this abstract state is still a nice summary that's going to allow the robot to sort of focus on what's important at the abstract level. So that gives us this abstract state space, but we're not done because even this abstract state space is combinatorially complex. There's many, many possible abstract states. So we're going to introduce another kind of abstraction, which will be a kind of action abstraction, which I'll refer to as skills, which will allow us to reason about what abstract states are reachable from other abstract states. So these skills will transition us in the abstract state space. So skills are going to have what are called operators. So for anyone familiar with classical planning, PDDL, strips, these are the kinds of operators that I'm talking about here. But for anyone who hasn't seen these, here's an example of an operator for the skill of picking from the table. So an operator has arguments, which are placeholders for objects. So for example, we have placeholders for the specific block and the specific robot that we're going to be using to pick that block. An operator also has preconditions, which say what needs to be true in the abstract state in order for us to consider using this skill. So if we're picking a block from the table, then the robot's gripper needs to be open and the block needs to be on the table. And finally, we have effects, which say what will change in the abstract state if we are to do this skill. So we have add effects, which get added to the abstract state. In this case, we'll be holding the block that we intended to pick. And we also have delete effects, which are what gets removed from the abstract state. So in this case, the robot scripper will no longer be open and the block will no longer be on the table. So this is all sort of lifted in the sense that we're not talking about specific objects, but we can take this operator and then we can substitute in whatever object we want to get this ground operator. For example, we can substitute block 1 in a particular robot gripper, and then we get this ground operator that's talking specifically about picking up block 1 with a particular robot gripper. And once we have these ground operators, then what we get is this abstract transition model where we can run our predicates on the current abstract state to get a current abstract state. And then we can look at our operators and say, okay, which preconditions hold? And among those, anticipate what the next abstract state would be under the effects of those operators. And then we can start to do this reasoning and planning in this abstract space. So why am I taking us down this particular path of using these predicate-based state abstractions and these operator-based action abstractions when there's a big family of other kinds of abstractions that one might consider? Well, the reason is if we have these particular kinds of abstractions, then we can take advantage of these very powerful solvers that have been optimized over several decades in AI planning. So for example, here are a couple of problems that are solved very easily by some of these AI planners. We have a block scroll problem, a Sokoban problem, and a tower of Hanoi problem. The one on the right is it's finding a plan of length 579 in just a fraction of a second, running on a regular laptop, just downloaded from the internet, and just running in a fraction of a second. So yeah, these are very powerful solvers, and if we can use them, then we're already doing very well. So once we have these predicates and operators, we can take advantage of them. However, we're not done even though we have these planners, because we haven't yet decided what actions the robot should take once we have this abstract plan. So to figure out what actions the robot should take, what we'll do is we'll take this abstract plan coming out of the symbolic planner, and we'll set up this constrained optimization problem, which says, find me a trajectory of low-level states and actions that's consistent with the abstract plan that came out of the symbolic planner. So we have these constraints that make sure that this trajectory optimization problem is sticking to this sort of sketch that's coming out of the symbolic planner. And we also need to make sure that the transitions are valid under the environment dynamics. So I refer to this as bi-level planning because we're doing planning at two levels. We're doing the symbolic planning at this high level, which gives us the abstract plan, and then we're doing this continuous optimization on the lower level, which tells us finally what actions the robot should take. And bi-level planning is a simple kind of a broader family of techniques called task and motion planning, and you can check out our survey paper for more context. So task and motion planning descends from some seminal work in the 70s on Shaky the robot and A-star search and other really foundational work at SRI and other places. And one of the ways that we've made progress over the last many decades is we're now able to solve much longer horizon problems than we were able to back then. So the robots can operate autonomously much more than they were able to in the 70s. And we also are able to solve a much wider distribution of problems. So, Shaky solved basically one kind of problem. Now we can solve a much broader family of techniques. But the generalizability of task and motion planning is still quite limited because it relies on these domain-specific models to be hand-designed, especially the predicates and the operators that I referred to before. So that motivates my work on learning these models instead, learning to make this kind of task and motion planning possible. And I'm going to tell you about that work now. So this is a kind of learning to plan. We're learning the models that are needed to do this kind of planning. And what we specifically need to do is learn predicates and operators so that when we use them as constraints inside of bi-level planning, we plan efficiently and effectively. So how can we go about this? Well, let's start by considering an easier version of this problem, where suppose that somebody's handed to us predicates for now, and all that we need to do are learn operators. And we're going to be learning from full task demonstrations like the one that's illustrated in this video. So we have predicates and we have these demonstrations, and the question is, how can we get operators? So we'll do a simple thing, which starts by taking these full task demonstrations and splitting them up into sort of the key frames where we ultimately want a new skill to start. So there's many ways that we can do this. In practice, we often look at changes in context between objects as the signal that we're using to do this kind of temporal segmentation, but there's many other kinds of techniques that one might use here. Once we have these segmented trajectories, we'll take the predicates that we're assuming are given for now, and we'll apply them to each of the key states in these segmented trajectories and get the corresponding abstract states. And then we'll just look at subsequent abstract states, and we'll see what is changing in between these abstract states. So we'll look at these differences between the abstract states. And you can already tell how these differences are going to correspond to the effects of the operators that we're going to finally learn. So we'll look at these differences, and then we'll use these differences as a signal to split up all the transitions that we have across all the demonstrations that we have into these clusters or sets of transitions. And we're doing this on the basis of the differences. So two transitions will belong to the same cluster here if they're equivalent up to object substitution. So for example, if we had one transition that resulted in holding the hammer and another transition that resulted in holding a bucket or something, we would put those together into the same transition set here. And once we have these transition sets, then we can get operators almost immediately. So the effects of the operators are read out exactly from the differences. And to determine preconditions, all that we'll do is we'll look and say what's in common among all the abstract states in the initial states of all the transition sets and take a big set intersection to arrive at preconditions. So from each of these transition sets, we ultimately get one operator. And this is all that we need to do this kind of operator learning. So let's now broach the harder question, which is, well, okay, we're not in practice given predicates. How can we learn predicates as well? And to address this question, let's start by considering an easy version of this question, where suppose that somebody has handed to us now a data set that looks something like this, where we have these states and we have these ground predicates, and we also have these labels saying in these states, these ground predicates do hold or they don't hold. So if we have this nice data set given to us, then we're happy because we could take advantage of whatever supervised learning technique you might want to use to learn the predicate classifiers. You can use neural networks, so you can use your favorite binary classifier. There's a little bit of care that we need to take to deal with the fact that these are relational classifiers rather than standard classifiers, but there's easy ways that we can deal with that. The downside of this entire premise, though, is that we need to commit to whatever predicates are just appearing in this data that we're being handed. And if they refer to natural language things, there's no guarantee that these kinds of predicates are actually the ones that we want to use for planning, if we're going to use these predicates as constraints for planning. And there's the obvious limitation that we need to be given this data in the first place, and that's kind of a lot to ask if we're going to be doing this kind of learning during deployment. So I want to instead consider a harder version of predicate learning where we're just going to be given the same full task demonstrations that we're going to be using for operator learning. And we're going to leave it up to the robot what predicates it wants to invent entirely, their structure, their number, their classifiers, everything. If we can do this, we'll be happy because this requires far fewer assumptions than the previous paradigm. And there's also the hope that the robot, since it's deciding what predicates it's going to learn, it can pick the ones that are explicitly optimized for efficient and effective planning. But this is a much harder problem now because we're lacking all that nice supervision, but it's a problem that we have some ideas about how to address, and so I'll tell you about that now. So to make progress here, we're going to address predicate learning as a kind of program synthesis, where we can look at these example predicates and say, well, those are simple little programs. I wonder if we can automatically synthesize predicates that look something like that. And we'll do a very simple kind of program synthesis, where we're going to start by defining this domain-independent grammar of candidate predicates, and then we'll just generate a pool of those candidates from that grammar, and we'll ultimately just subselect predicates to keep from this large pool of candidates. So here's our pool, and we're going to start now with an empty set and gradually add one predicate at a time. And we're going to be performing this hill climbing search, which is at each step going to select a predicate to keep. So we start with this empty set, and then gradually add one predicate at a time to the pool. And as we're doing this hill climbing search, the fundamental question is, what is this objective that we're using to decide what predicates are the ones that we want to finally keep in our final predicate set? And this is really the question that's fundamental to state abstraction learning in this context. So to answer this question, we can look at the broader literature on state abstraction learning and try to see if we can use existing ideas. So for example, one common idea in learning state abstractions is reconstruction, which basically says state abstractions are useful if they're as good as possible at reconstructing the original states after we perform the abstraction. There's also ideas in the MDP literature on things like homomorphisms and bisimulation. But the problem with all these is that they're not sufficiently tied to what our real objective is here, which is that we want to learn predicates that when we use them for bi-level planning is as efficient and effective as possible. So our real learning objective would have us take a candidate predicate set and take the demonstrations that we have and actually run our operator learning on the demonstrations with the candidate predicates to get operators. And then we would use those operators and these predicates to try to actually solve tasks from the distribution that was demonstrated to us and run the entire bi-level planning procedure and record the amount of time taken by this bi-level planning procedure, and then note whether planning succeeded and how much time planning took. So we could do this for one task that was demonstrated to us, we could do it for a second task that was demonstrated to us, and we could look at all the demonstrations that we have as being important and run our planner over all of them and record whether the tasks were solved and how much time the planner took. And at the end of the day, we would have an objective that combines these and says, basically, I want to solve as many tasks as possible, and I want to do so as efficiently as possible. But as you might expect, the problem with this real objective is that it's completely intractable to actually do this inside of hill climbing. It's just way, way too slow. So what we're going to do instead is we're going to introduce a surrogate objective, which will be faithful to this real objective, but it's going to be much more tractable to actually evaluate. And we'll start by noticing that the really intractable part of all of this is this inner continuous optimization problem. This is not really tractable to run, especially early on when we have predicates that are not providing rich enough supervision. On the other hand, we can run our symbolic planners because these symbolic planners are very fast, so we can explicitly measure the time taken by that symbolic planner. So to deal with this intractability, what we'll do is we'll use the demonstrations that we have available to come up with an approximation that sort of bypasses this continuous optimization. So specifically, what we need to be able to do is estimate the probability that if we did run that continuous optimization, what's the likelihood that we would actually succeed without actually running it? And we have this very simple formula which allows us to have a coarse approximation of that quantity. So what we'll do is we'll look at the abstract plan that came out of our symbolic planner, and then we'll look at the demonstration that we have for the same task, and we'll look at the number of steps in each of them. And we'll just compare those costs, those numbers of steps, and we'll say that the probability of refining or successfully solving that continuous optimization problem is higher if those two costs are more similar. So we're just looking at the cost of the demonstrations here. And the intuition is that if we have an abstract plan that appears to be cheaper than the demonstration, then that's kind of suspicious. It's too good to be true. Why wouldn't the demonstrator have shown us this abstract plan if such an abstract plan were actually possible? On the other hand, if we have an abstract plan that's more expensive, then that's just plain bad. So this is kind of the core intuition that's driving this surrogate objective, and the surrogate objective is really what's driving this overall predicate learning procedure. So that really completes our predicate learning approach, and we can take a look at some of the predicates and operators that get learned with this overall approach. So it's very small font, but just to give you kind of a sense of the quantity, so there's about 18 predicates in the top left there, and the rest are operators that are learned with those predicates. And since these are programs, we can easily inspect them and understand that they refer to intuitive concepts in this tool use domain, like nail is being held by the robot, or a screwdriver is small enough that the robot can grasp it. We also see that planning with the predicates and operators that are learned is very efficient in terms of the time taken by the planner. And we're running now on planning tasks that involve many more objects than we're seeing in the demonstrations. So block stacking problems with many objects, to blocks to stack, and a painting domain with many objects to paint and put away. And compared to some baselines, like biosimulation being the best abstraction learning baseline that we compare against, we're planning much faster using the predicates that we learn. And we also see that sometimes when we plan with the predicates that we learn, we find we plan faster than planning with predicates that we write down by hand. And I'll show you an example of that in a moment. Another cool thing is that the predicates that we learn are task aware. And so what I mean by that is, suppose that we have, as part of this painting domain, that we need to put away these painted cylinders into this shelf. And the shelf has a ceiling. And if all we ever need to do is put these cylinders away into this shelf, then maybe we'll learn a predicate which is called holding by inspection of the program, which just encodes whether the block is held or not. But now suppose that we change the task distribution so that sometimes we need to put those cylinders away into the shelf, but other times we need to put it away into a box. And this is a box now that has an opening on the top and it has walls on the side. So now there's this important distinction between whether we've held the cylinder from the side or the top, because if you hold it from the top, then you can't actually place it into the shelf. There would be a collision with the robot's wrist, whereas if you held it from the side, you can't actually place it into the box because of the sides of the box. And so our predicate learning procedure automatically discovers that this is the important distinction that's worth modeling at the abstract level, and we learn two different predicates for holding now, one for holding side and one for holding top. And a final cool thing is that the predicates that we're learning are planner aware. So they're aware of the planner that we're actually using at test time. So for example, here's another block stacking domain now on a real robot. And if we run our entire pipeline with a certain AI planner, we find that the predicates that we learned are very standard kinds of predicates that have been used for a very long time in these kinds of block stacking domains. But when we changed the AI planner very slightly, we found that we learned a different set of predicates that was almost the same, except that nothing above predicate was split up into two. And at first we thought, okay, maybe those are just two predicates that are sort of equivalent to nothing above, or maybe this is even a local optimum in the hill climbing search that we got stuck on. But then we noticed that with this second AI planner, planning with this second set of predicates was actually 30 times faster than planning with the more standard set of predicates. And it's due to some like weird quirks in how this AI planner is actually working that our learner has discovered as being important. So this really speaks to the fact that we're learning these predicates and operators that are explicitly optimized for fast planning. So altogether what this gives us is a way to learn these state abstraction predicates and these operator-based action abstractions for bi-level planning. But at this point, I want to unpack something I've been hand-waving about so far, which is what is actually happening inside this continuous optimization box. So let's think about how we would actually go about turning this abstract plan into low-level actions that the robot can execute. So one thing that we might do is extend the definition of a skill so that we don't just have these operators which tell us what abstract state transition we're trying to achieve, but now we'll also have these policies which tell us how the robot should actually take actions towards achieving that abstract transition. And we've seen that when we're learning, these operators will often be symbolic and the policies will often be more low level that are interfacing with continuous states and actions, and we often use neural network techniques here. So if we have these policies, the idea is that the planner would output a skill, and now the skill would take in a state and it would output a low-level action that the robot can execute, and then it would get another state after executing the action, and the skill would propose the next action, and it would operate in closed loop with the low-level environment until we actually achieve the abstract transition that the skill is designed to achieve, and then we can move on to the next skill. So this all seems sensible. And here is one example of what these skills might look like. So this is a pick from table skill, and we see this is a policy running now, and there's many actions being taken by the robot to achieve one abstract transition, which is like holding the block that we're trying to achieve. And also I should say that the policies are relational, so the same policy here is being used at first to pick block 1, and which is the green block, and then to pick block 2, which is the blue block. So why did I go through the trouble of describing this as a continuous optimization problem if all that we're going to do at the end of the day is use some kind of reactive policy? It seems like we just hide all the complexity in that policy. Well, it's fine for block stacking, but when we move into more complicated domains, we'll find that the abstractions might be kind of liars in the way they're suggested by this dog trying to get this stick through the door while ignoring the geometry of the stick. So to better explain what I mean by these abstractions might be liars, let's take a look at this example from Danface Yu and colleagues, where there's two things that you might want to do in this tabletop domain. So one thing you might want to do here is get that red block onto that green platform. And to do that, you need to use this hook as a tool because there's this reachability limitation on the robot scripter which says it can't go beyond that transparent wall. So first, the robot needs to pick up that tool and then sort of pull the red block from beyond that transparent wall, and then pick it up and then put it onto the green platform. And the second thing you might want to do in this domain is get the blue block onto the green platform. And for this, you again need to use that hook, but this time you'll grasp it at the top, and then you'll poke the blue block through the tube and pick it up and then put it onto the platform. So in both cases, we're using this hook as a tool, but in the first case, we had to grasp it at the bottom, and in the second case, we had to grasp it at the top. So let's think through what it would be like to apply the kinds of skills that I've described so far to a domain like this. So perhaps we would have an operator for pushing out of the tube, which looks something like this, which says if we're holding the hook and if the block is in the tube, then we should be able to get the block out of the tube. If we find ourselves in a state where we just grasp the hook from the top, then everything's great. We can, in fact, get the blue block out of the tube. But if instead we've just grasped the hook from the bottom, it's in this sense that the abstraction is kind of a liar, because we are holding the hook and the blue block is in the tube, but because we've grasped the hook at the bottom, it's not actually possible to get that blue block out of the tube because of the details in the low-level state. So what should we conclude from this example? Well, one reasonable conclusion is that the predicates that we have to describe the preconditions of the operator are insufficient. And maybe what we should do is learn new predicates that distinguish between holding top and holding bottom. And that's very reasonable. We've seen that we can do that. And I think in this simple example, that actually is kind of the right answer here. But as we move to more complicated kinds of environments with more interesting kinds of geometry and kinematics, we'll find that we don't want to force all the complexity to be fully captured at the abstract level. We want to, be able to do better than that. So another reasonable conclusion would be actually the issue is in the policy. And maybe what we need to do is learn a better policy that, for example, involves regrasping the hook, and then after the hook is regrasped internally to that policy, then we can accomplish the abstract transition. And I think, again, this is a reasonable thing, and we would like to be able to learn better policies, but we don't want to, again, force all the complexity now into policy learning. So I want to pursue a different kind of interpretation, which says the issue here is really in the planner. This planner is trusting the abstractions too much. It's moved too far away from viewing the abstractions as a kind of guidance for low-level planning and reasoning. It's ignoring the low-level entirely. And I think we should go back to this view of abstractions as a form of guidance. So let's unpack this a little bit and see how we can go back to viewing these abstractions as a kind of guidance. So the abstractions might be liars in the way that I've said, but that's okay. All models are wrong, but some are useful. And I think these kinds of action abstractions can still be useful. But to make them useful, we're going to extend the definition of a skill a little bit further, and we're going to introduce this continuous parameter space into the skill policy. And this continuous parameter space is going to give us basically a degree of freedom that allows us to accomplish the skill in many different ways. So for example, if we're talking about picking a tool, then we might have this sort of infinite space of possible grasps of the tool, which we can then accomplish picking in this infinitely many different ways. And the reason this is nice is because now during planning, we can optimize in this parameter space and try to find settings of these parameters that will satisfy the entire abstract plan. So for example, if we at first consider a parameter where we've grasped the hook from the bottom, then we'll see later on we're not able to accomplish the rest of the plan. And so eventually in our optimization, we'll go back and we'll consider a different parameter, which might have us pick the tool from the top, and then we will be able to satisfy the rest of the abstract plan. And you'll also see that these parameters are being proposed by this new component called a sampler, which is something we typically learn alongside a policy and an operator for a skill. And these samplers will give us reasonable choices of parameters that we can use during optimization. So what we'd like to do is be able to learn all of the components of the skills. So we want to learn samplers, policies, and operators. And we want to learn these in a way that allows the robot to move flexibly between different abstract states and is useful for bi-level planning. And so learning these kinds of skills for planning has been another theme of my work. And we have now this kind of family of techniques that are all sort of mutually compatible that we can use to learn these skills in a number of different environments. And a key theme throughout all this work is learning these skills from a little bit of data, often demonstration data, in a way that generalizes a lot. So one of the key ingredients that allows us to do this kind of data efficient generalization is this neurosymbolic structure kind of learning. So we've already seen a kind of operator learning, which we can use to effectively learn these symbolic operators, and we can broaden the family of operators that we're learning by drawing on inductive logic programming, among other techniques. And on the policy and the sampler side, we often use neural networks, but there's other choices that one might make here to learn these kinds of representations that allow us to do this reasoning at these lower continuous levels. And we always learn these models in a relational way that allows us to generalize to new objects. So we often use ideas from relational deep learning. So, for example, what we can do with these kinds of skill learning techniques is we can start with demonstrations from something like a coffee preparation domain, where we start by heating up that mug on that hot plate, and then we pour coffee into a cup. So given about 50 to 200 demonstrations of tasks like that, then we can learn skills that generalize to new low-level states, to new and more objects, and to new and harder goals. For example, instead of pouring into one coffee cup, we can pour into many coffee cups, or 3 in these examples. And we've shown that these kind of skill learning techniques work across a number of different kinds of domains, and we have empirical results as well, showing that our approach does better in terms of data efficiency and generalization than a number of different baselines, especially graph neural network kinds of baselines, which are a good choice because they're relational and they're able also to generalize over objects. One final kind of advantage of this very structured kind of learning is that it's straightforward for us to combine learned skills with ones that we know how to write down by hand. So for example, we have a good understanding of motion planning that we can use to design navigation skills. And so we can have this manually designed navigation skill and combine it with something like a door opening skill. And then we can use bi-level planning with these combinations of learned and manually designed skills to solve these very long horizon tasks that involve getting from one room to another while avoiding obstacles and opening doors along the way. So altogether, this family of techniques is this pipeline that's all sort of mutually compatible that we've built up over a series of papers. And what this represents is the first kind of unified system for learning models that can power a task and motion planner. So that's a little bit about my work on learning to make task and motion planning possible. I have additional work on learning to make TAM fast, trying to improve us on this time horizon axis as well. I don't have time to get into it today, but we have a number of different kinds of techniques. For example, we can use large language models these days, and we can learn more classical techniques as well to learn a number of different kinds of models that make planning fast and have the robot sort of get second nature as it continues to see the same kind of problems over and over again. In the last part of the talk, I want to just briefly mention some work on not just learning to plan, but also planning to learn, where the robot's going to use its initial ability to plan reasonably well to collect additional data online and then use that data to get better at planning. So this goes back to my initial motivation, where we want to have robots that are capable of learning to specialize during deployment. And the work that I've talked about so far is kind of learning that I sometimes call like Eureka-style learning, where we're learning these high-level concepts from just a little bit of data that generalize a lot. But there's a very different kind of learning that I think is equally important, which is more like learning through practice. So we want to have robots that can do something like when humans, are learning to juggle or learning to play piano or ride a bicycle. We're not just watching a couple of examples of those things. We're practicing these things to really become experts at them. So we want our robots to be doing a similar kind of learning through practice. When we're talking about learning through practice, the key technical question is, how should the robot decide what to practice? So in the reinforcement learning literature, this is a question of exploration, and it's also very related to active learning and machine learning. So I want to tell you now about a recent project that's under review right now with folks at the Boston Dynamics AI Institute, where we're looking at learning these kinds of skill samplers through practice. So the story here again is that we're going to have these robots that are coming to the factory and shipped off to many different kinds of deployments. But for the sake of this project, let's assume that the robot's coming to us with a certain library of general skills, and those skills will also have these sort of parameter priors that propose reasonable but imperfect parameters for the skills. So for example, maybe the robot would have a grasping skill, which has this prior that sometimes succeeds in grasping, but other times doesn't, depending on the particulars of this hammer being on the rack. And maybe we would also have a place skill that comes with the generic place parameters, which varies, for example, the displacement of the robot's gripper with respect to the bucket, and sometimes for certain parameter settings it works and sometimes it doesn't. So what we'd like to do is have our robot autonomously plan to practice and get better at these parameter selection policies autonomously. And we want to do something like this dog who's maybe planning to practice the stick throwing skill that it's come up with as being interesting. So we want our robot dogs to be doing a similar kind of planning with practice, maybe a bit more complicated. So perhaps the robot decides that it wants to practice the skill of sweeping. And to even get to the point where sweeping is possible, it needs to plan many, many steps to get to a state where sweeping can be done. So the technical question that we're focusing on here again is how should we choose what to practice? In this case, how should we choose what skills in the library of skills that the robot has are worth practicing? And we want to do that in a way that maximizes our future task success. So to start to answer that question, we're going to introduce a kind of skill competence, which is like the probability that a skill will achieve the intended abstract transition that it's designed to achieve. So for example, in the case of grasping, maybe if we half the time succeed in grasping the object, then maybe that initial parameter policy has a competence of 0.5. So if we have these known competences, which we don't have in practice, but we can estimate, then we can introduce these competences into the planning itself to try to find an abstract plan that's most likely to succeed at the abstract level. And we can turn these competences into basically costs and use a cost-aware planner to try to find this maximum likelihood plan. So how should we decide what skills to practice? Well, one intuitive idea, which is actually the thing that we started with before it broke, is maybe we should practice the skill that we're currently worst at. So let's focus on what's failing, or the skill with the lowest competence. But we quickly discovered that the problem with this approach is we might end up practicing a skill that actually can't get any better no matter how hard we practice it. And the other issue is that maybe the skill that we're practicing is one that's actually not that important or even unnecessary for the tasks that are relevant or being given to us by a person. So that led us to this alternative approach, which we call estimate, extrapolate, and situate. And the idea here is that we want to practice a skill whose improvement would lead to the greatest overall improvement on the entire task that we care about. And we'll do this in 3 steps. So first of all, we'll look at the skills that we have, and we'll estimate the competences of each skill, asking how good are each of these skills right now. And then we'll extrapolate those competences. So we'll say, if hypothetically we did practice this skill, how much better do we expect to get at that skill through practice? And then finally, we'll situate the skill in the distribution of tasks. So we'll say, if we did hypothetically practice this skill, then how much better at the overall task distribution would we get? So to do this estimation and extrapolation, we have this graphical model, which involves Beta and Bernoulli distributions to jointly do this estimation and extrapolation step. And to do the situate step, we use that symbolic planning with competence cost that I briefly mentioned before. So let's take a look at an example of what this looks like. So here's a kind of toy domain to illustrate the key ideas. So this is a robot that, hypothetically has just come from the factory with a certain set of skills and samplers. And we said to the spot robot, please put that ball on this table. And so given the skills that it has initially, it thinks that the best way to accomplish that goal is to pick up the ball and put it onto the table. But it doesn't know that that table is actually slightly slanted in a way that makes putting the ball on the table directly impossible. So after it fails, we now give Spot free time, and it's completely up to the robot what skills it's going to practice, and it has to plan to practice them. So here it goes in its free time, starting to plan to practice, and at first, it's going to be very optimistic about what it can get better at, and it's going to think, if I just keep practicing placing that ball on the table, then over time I should get better through practice. And so quantitatively, it has this estimate of current competence, which it knows is not that great, but it thinks that extrapolating, if I just keep practicing, then the competence should improve. It also knows that this place ball on table is in its current maximum likelihood task plan, so that's why it's worth practicing this skill at this moment. And it's constantly estimating and extrapolating all these skill competences that it has in its library. So it'll keep planning and practicing, and it'll keep focusing on placing the ball on the table for a little bit longer. And again, it has to replan when it fails to grasp. And after one more try, it's now going to realize, okay, I'm practicing putting the ball on the table, and no matter how hard I'm practicing, it's not getting better. So it's going to update its extrapolation for place ball on table to be less optimistic. And now, given that more realistic estimate, it's going to update its maximum likelihood task plan and try to accomplish the original goal in a different way. So specifically, it's going to try to use this ring that we conveniently left in the room to kind of set up a stable support on the table, which the robot can then put the ball into that ring. So now it has this different plan, and now it's going to try to get the ring instead. And so it'll try to put that ring on the table, but turns out that the table is actually smooth on the right-hand side, and so the ring falls off if you try to put it on the right-hand side of the table. So far, nothing's working, so it just goes back to trying the ball, and then it'll just kind of, try the ring again. And this time, putting the ring does work, and practices placing the ring once more. And so finally, it has succeeded in placing the ring, and then it finally gets the ball on the table after all that effort. So now we've seen this one example, but this is still happening in the robot's free time. And so it will continue practicing autonomously and without us intervening whatsoever, except to change its battery once in the middle. And we can just watch it practice for about 3 hours. So we'll see a very sped up video about 100x. So here goes the robot. And what you'll notice is that it's spending quite a lot of its time planning to practice placing the ring on the table, which is what we hope to see, because that's the thing that it can get better at in service of accomplishing the original task goal. So it's going to spend a ton of time practicing placing the ring on the table. And after all that, we can then come back and reevaluate the robot and see, did it actually get better at accomplishing the task that we care about? So we can say, once again, hey, Spot, put the ball on the table. And we'll see that it first of all goes for the ring, which is good, and then it does that really nice placement of the ring on the left side of the table. As a little bonus, we can check whether Spot is robust to a certain kind of adversarial intervention, inspired by shaky videos for anyone who's familiar. So Spot is pretty robust. And I want to also show you a second environment, which is a little bit less toy, although it involves toys. So it involves a basketball and an ambulance toy. And the idea here is that we're going to tell the robot that we wanted to sort of clean up after maybe a child who left those toys on the table. So we'll say, hey, Spot, put the toys in the bin. And again, this is sort of at the beginning when the robot's just come from the factory and it doesn't know how, it's not specialized to this environment yet. But it knows already that using planning that it needs to move that chair out of the way to access the toys. And it also knows that sort of the best way to accomplish this is using broom, because that's the shortest way to get both toys into this bin. But its sweep is not calibrated to this environment, so it needs to plan to practice sweeping. Oh, I'm sorry, let me skip ahead. Okay, so here it goes planning to practice sweeping. And this is once again just in the robot's free time. It'll gradually get sped up more and more, but you'll see that it's decided automatically that the thing that it should be practicing is sweeping, and is going to repeatedly plan and practice to collect more data about sweeping and get better at sweeping over time. Once again, like 2 or 3 hours. So after that, we can come back and we can reevaluate the robot again. We can say, hey, Spot, put away the toys. And it will go through the same procedure of moving the chair out of the way first, grabbing that brush, and then will it succeed? We'll find out. Yes. And we can do some gremlin testing once again. This time I'm the one that's dressed up as a gremlin. So you see I put that basketball on the shelf, which is going to be too high for the robot to grasp directly. And it can see out of his cameras that the ball is on the shelf, it's not in the bin. And so it's going to use this platform dragging skill that I previewed earlier to try to get that ball. All right. So that's a little bit about my work on planning to learn. And the hope is to create this virtuous cycle of learning and planning where each is improving the other. And with that, that concludes sort of the technical meat of this talk. And now is the fun part where I get to acknowledge all the great people that have made the last 6 years so wonderful. And to start the acknowledgments, I wanted to take inspiration from Leslie and Tomas's lab, where we often announce lab meetings by including either a riddle or a poem. And so in that spirit, I'm going to start with a couple poems. So first, a poem for Leslie. In my grad school quest, an ambition was clear, to work with Josh, whose research I held dear. At the time, Leslie Cabling was not in my sight, but she reached out to my great delight. I quickly learned that Leslie is the creme de la creme, the best academic and mentor and friend. Her knowledge is vast, her expertise boundless. The number and ways she would help me are countless. She's not one for political games. Her quest for deep insight is always the same. Citations, grants, fame, and fortune are boring. Why exploit when you could be exploring? Her foresight is so far and her thinking is so fast, the field is still catching up to her work from 30 years past. If the trend continues, then the mainstream camp by 2054 will come around to TAMP. The people of their stature, Leslie and Tomas, somehow find time to tinker with BOSS and dynamics robots and other low-level code. When people hear that, their heads usually explode. Leslie's mentorship is so reliable. Her care for her students is undeniable. I feel so fortunate to have gotten 6 years of meetings and laughter and advice on careers. As I step forward with much more to learn, I will ask what would Leslie do at every turn. So here's to Leslie, the mentoring state-of-the-art, a role model, a mentor, and a hacker at heart. And now a poem for Josh. Before I met Josh, he was just a legend, a towering figure at the cutting edge and an inspiration to so many, including me. I couldn't wait to work with him at MIT. As we started to collaborate, it seemed like a dream. I still couldn't believe I was part of his team. In my first year, the lab went on a retreat. Josh sang and played piano until 4 a.m. and I had a front row seat. At that point, my life seemed truly surreal, but I learned that with Josh, singing and laughter are just part of the deal. So is unbelievable energy and constant inspiration, and ideas that merit a standing ovation. Josh's knowledge is unbelievably broad and deep. It's a wonder that he ever finds time for sleep. To say that he's a field leader is not enough. He's not just in the field, he invented this stuff. Josh's encouragement and guidance has meant so much, and when I've been stuck, his advice has truly been clutch. Graduate school was much easier with Josh on my side, a mentor in whom I could always confide. Josh has many collaborators, and I hope that I will remain among them, so this is not goodbye, but see you on the other side of the academic fence, assuming, of course, that I pass this defense. And I'll spare you from any further poetry, but I have many others to thank, each deserving of their own poem, starting with Tomas, who is sort of my secret bonus advisor. Tomas and Leslie jointly run the Learning Intelligence Systems group, so I've had the privilege of meeting with him along with Leslie and Josh over the years. And Tomas is just incredibly reliable and so helpful at all the different levels of abstraction that go on in research, from high-level brainstorming to low-level technical stuff to writing. He's just so helpful and so reliable. People like to point out that Tomas is always quick with a joke, especially dad jokes or bad jokes, depending on your perspective. And that's absolutely true. But I think that points to the fact that Tomas is never taking himself too seriously, which I really admire. But he also does take his work very seriously, which goes towards explaining why he's such a towering figure in robotics and beyond. And my other secret bonus advisor is George, who was really somebody that got me excited about AI and robotics in the first place. I remember that when I was an undergrad taking my first ever intro to AI class, we had a guest lecturer come in and tell us about some work that George was doing at the time on skill training. And that was the first time that I remember thinking to myself, oh, wow, this is actually pretty cool stuff. I wonder if I might want to do this in my career. I also, over the years have just kept returning to his papers. Every time I'm thinking about a new project, there's of course like 3 George papers on the subject, and I've, returned to his skills to symbols work over and over again. And every time I find something I missed the first time. He's also sort of famously busy, but also somehow finds time for everybody, somehow including me. And I feel very fortunate for that. And I hope we can continue working together. Over the 6 years at MIT, I've collaborated with so many wonderful people, but there's a couple of people who I've worked extremely closely with, and I wanted to acknowledge them. So starting with Kelsey, who was the first really close collaborator and mentor to me when I started out from day one in grad school. And we quickly discovered that, we don't only have common research interests, but we also are very similar people, which made it quite easy to collaborate and also to be friends. And I'm very grateful that even though we're now geographically separated, we still keep in close touch and talk almost every week. The next person that was majorly influential in my career was Rohan, who I worked with incredibly closely. And he sent me this video, his own free will. He sent me this video. I'm not going to provide any context because I think it's better that way. But Rohan and I worked extremely closely together for about 2.5 years before he graduated. We sent literally hundreds of thousands of Slack messages to one another. And my PhD definitely wouldn't have been possible without working with him very closely. And we were also very close friends, which I am very grateful for. And most recently, I've had the pleasure of working with Nishant, who was the first gremlin in the video that you saw before, especially as both of us were interning at the Boston Dynamics AI Institute. And Nishant has been a dream to work with. I remember he was obviously special when he was an undergrad, and we were super excited when he joined our lab. And he's really become my go-to person for all things research. For example, he's manning the Zoom right now because he's a person I trust to do that. And he's just super brilliant, super talented, super reliable, and I'm very grateful to work with him. Some of the best times that I've had in my PhD have been as an advisor to many wonderful undergrads and master's students, and I'm so proud of each of them. I feel very fortunate that in addition to doing great work, I also like them all personally, which has been so wonderful. I wish I had time to acknowledge them each individually, but it's really been some of the best times that I've had in grad school is working with them. I also want to thank very much all the members of the labs that I've been a part of, so the Learning Intelligence Systems group with Leslie and Tomas, as well as friends and collaborators in Josh's group, the Computational Cognitive Science group. And over the past year, it's been a great pleasure to intern at the AI Institute, and I'm very grateful to see so many folks from the Institute here today. And I've also really enjoyed working with folks from IBM. I also want to thank a couple dogs, mostly my dog Namsi, who's been with me throughout grad school and supported me in his own way, and also thank the robot dog Spot, which definitely has been helpful in getting a job. I also want to thank my family, my mom, my dad, and my sister, as well as newer additions to my family, Terry and my future in-laws, Sidna and David. They've all been incredibly supportive throughout my entire career and throughout my life, and I want to especially acknowledge my mom, who passed away in the second year of my PhD. And lastly, I want to thank my fiance, Hannah, who has been my rock throughout the entire PhD, starting with moving to Boston so that I could do the PhD, to proofreading every word that I ever wrote during the PhD, to providing unbounded emotional support through all the highs and lows. And I'll just say that there's been a lot of exciting developments over the past couple of months, but absolutely the most exciting is that we're engaged, and I'm very excited for our future together. Thanks. I'll take questions.
Now I know the secrets of wonderful writing. Okay, yeah, good, I got it. Question, anybody have a question? Somebody.
Stephanie.
Did you, the skill for dragging the thing, did you learn that skill from demonstrations, or did you program that?
We programmed that,
And
yeah.
why did you do?
It was easier. Yeah, we'd like to learn that, yeah, and maybe you and me are working on that now. That'd be awesome.
Why is it still easier to program?
So it's easier because we did not need a super robust dragging skill to make that video. We just needed one that worked in that room. But if we want to actually have a robust dragging skill that could truly be used in a more general way, then we would want to learn that because it is hard to program.
I have a two-part question.
Yeah.
The first one is, could you speak to the role of uncertainty and how well these like object-centric representations work? And the other part of the two-part question is two enough as far as like bi-level goes? Like, would you like, could you do more levels of abstraction, and would that get you anything, or is too?
Yeah, great. I'll repeat the question for anyone. So first question was, can I talk about the role of uncertainty in this system, which definitely has not played as central of a role as I would like. So there's uncertainty at the perception level, which first of all could be that we don't see objects all the time, so we should have some uncertainty about the location of objects or even the existence of objects, for example. And then we should also incorporate that kind of uncertainty into planning. So we should, for example, be able to say, maybe in the refrigerator there's milk, I can't see it right now, but I have some uncertainty about that, so I should try to look around and take actions towards resolving my uncertainty about that. So in a partially observable kind of setting. There's also uncertainty at the level of transitions. So in the competence stuff that we were talking about at the end, that's a little bit of uncertainty measure, because a competence is basically our uncertainty about the skill succeeding. But